When writing computer programs, we spend a lot of time constructing expressions that mean what we want them to mean. So let's take a step back from writing programs and try to understand what it is we're talking about when we talk about the meaning of a computer program. We've said that an expression like let x equal 41 in x plus 1 evaluates to 42, that these two expressions mean the same thing. But so far, we've been pretty informal about why expressions have the meanings they do. But as programmers, it can be useful for us to have a formal, rigorous, precise notion of semantics, which is all about understanding what expressions mean. There are several ways we might try to provide a formal semantics for a programming language, but in this case, we'll be using a model known as the substitution semantics. The substitution semantics is based on a particular idea of what it means for two expressions to mean the same thing. In particular, that two expressions mean the same thing if one can be substituted for the other in any proposition and preserve truth. What do we mean by that? Well, say we had the expression 2 plus 3 times 4 equals 20, which is true. If we substituted the 2 plus 3 for 5, we'd get the expression 5 times 4 equals 20, which is also true. Moreover, we could take any expression and substitute 2 plus 3 for 5, and the truth of the expression would not change. And so therefore, according to the substitution semantics, 2 plus 3 and 5 mean the same thing. So, how are we going to formalize this idea of semantics in the context of a programming language? We'll do so by formally defining the relationship between expressions and what they evaluate to. Notationally, we'll provide judgments of this form. Anytime we write an expression p, a downwards arrow, and a value v, we take that to mean that the expression p evaluates to the value v. So let's take the syntax of OCaml and provide a semantics for determining what expressions evaluate to. What we'd like to do is to be able to take any expression of this language and provide a judgment to describe what it evaluates to. Let's start with the simplest case, integers. When we have a numeric literal, that is to say an expression that's just a number, like 1 or 2 or 3, they're already simplified, so they evaluate to themselves. We could write out some judgments to describe that. 1 evaluates to 1, 2 evaluates to 2, 3 evaluates to 3, and so on. But of course, there are infinitely many integers, so it's not feasible to write out a separate judgment for every possible integer. Instead, we'll write a general rule that we can apply anytime we need to write a judgment for an integer. The rule will look like this. We'll let the letter n stand for any integer. When we write the n with a horizontal bar over it, that represents the OCaml expression that encodes the integer n. So here, we'll say that n evaluates to n. In other words, if we have an OCaml expression representing an integer n, it evaluates to itself. We'll give this rule a name, rint, since it's a rule for how to evaluate integers. This rule is an especially simple rule, but we can use this notation to define other rules too. For example, let's come up with a rule for what the expression p plus q evaluates to. Here, p and q could stand for any expressions. They might just be integers, but they might also be more complex expressions too. What does the expression p plus q evaluate to? Well, it depends. In particular, it depends on what p evaluates to and what q evaluates to. We need to know those two judgments before we can answer the question of what p plus q as a whole evaluates to. When we evaluate p, we'll get some integer. Let's call it m. And when we evaluate q, we'll get some integer. Let's call it n. So what does p plus q evaluate to? It evaluates to whatever expression represents the number m plus n. This rule is a little more complex than the integer rule we saw before. In particular, in order to know what p plus q evaluates to, we need some further evaluation judgments. Those are indicated by these indented judgments to the right of the vertical bar. We need to know both what p evaluates to and what q evaluates to. And then the last line of this rule gives us the value that the original expression, p plus q, evaluates to. Since we're using this rule to describe how to evaluate addition, we'll call the rule R+. Let's see how we could actually use these rules to evaluate a specific expression in OCaml. For example, what does the expression 2 plus 8 evaluate to? Well, 2 plus 8 is an expression formed by adding two other expressions together, so we'll apply the R plus rule, which works for any expression p plus q. In this case, the expression p will be the left side of the addition, the 2, and the expression q will be the right side of the addition, the 8. So we can start by figuring out what the left expression p evaluates to. In this example, that's the number 2. What does 2 evaluate to? Well, according to our first rule rint, any integer just evaluates to itself, so 2 evaluates to 2. Likewise, for the right half of the addition, the number 8 evaluates to 8. So what does the entire expression 2 plus 8 evaluate to? It evaluates to the result of adding together the integers 2 and 8, which gives us 10. If we had an expression with multiple addition operations, we could use the same approach. We could evaluate the expression 2 plus 8 plus 5. Let's assume left associativity, so the left expression is 2 plus 8 and the right expression is 5. According to R+, to evaluate this whole expression, 2 plus 8 plus 5, we first need to know what the left side, 2 plus 8, evaluates to. We've already seen how we can calculate that. We evaluate the left side 2 to 2, then evaluate the right side 8 to 8, so the expression evaluates to their sum, which is 10. That's the left half of the addition for the overall expression. Now we also need to evaluate the right side, which is the expression 5. That's just an integer, so it evaluates to itself. So the left half of our addition evaluated to 10, and the right half evaluated to 5, which means this whole expression evaluates to the sum of those two values, 15. Similar to our addition rule, we could construct similar rules for binary operators like subtraction, multiplication, and division. Notice that in our division rule, we're specifying that the meaning of division in this programming language is taking the floor of the result of dividing one integer by the other. This is a choice we have to make when determining the semantics of the language. Other languages might make a different choice for how division should work. But still, these rules aren't doing too much yet. Where things really start to get interesting is when we try to define the meaning of a let expression that introduces a new name. Let expressions take the form let x equal d in b, where x stands for some variable name, d stands for some definition expression, and b stands for some body expression. What does this expression mean? In other words, what does it evaluate to? Intuitively, we know that the definition expression d has some value, and whatever that value is, what we'd like to do is take the body expression b and evaluate it. But we can't just evaluate the body immediately, since the body might contain occurrences of the variable x. Instead, we'd first want to substitute the value of the definition for any occurrences of x in the body expression, and then evaluate that new expression. Let's write that down formally using our rule notation. To evaluate the expression let x equal d in b, we first need to take the definition expression d and evaluate that. Once we evaluate the definition, we'll get some value. We'll call that value vd, since it's the value of the definition. Next, we'd like to evaluate the body expression b. But rather than just evaluate the body, we'll evaluate the expression we get when we take the body and substitute occurrences of the variable x with the value of the definition vd. This is the notation we'll use to describe substitution. It means we're taking the expression b and substituting what's left of the arrow, the variable x, with what's right of the arrow, the value vd in this case. Once we evaluate that expression, we'll get some new value vb, the value of the body. And that value is what this entire expression evaluates to, so it becomes our answer. This then is the rule rlet, our rule for how to evaluate a let expression. Let's try to apply this rule to an example. Here's an expression that we want to evaluate. Let x equal 4 in x times 2. How would we evaluate this expression? We have a let expression, so we're going to use our rlet rule, which indicates that a let expression has a variable, in this case x, a definition, in this case 4, and a body, in this case x times 2. We'll start by evaluating the definition. The definition is just an integer 4, which evaluates to 4. The next step of our rule is we need to evaluate the body x times 2, but with occurrences of x replaced by the value of the definition, which is 4. So instead of evaluating x times 2, we'll evaluate that expression, but with x substituted with 4, so we'll evaluate 4 times 2. And this is just a multiplication, so we know how to evaluate it. We evaluate the 4 to itself and the 2 to itself, so this whole expression evaluates to the product, which is 8. Just by following these rules, we've been able to determine what a let expression evaluates to. Let's take a look at the case of functions now. Remember that in a functional programming language, a function is just a value. So if we have a function expression with an argument x and a body b, it just evaluates to itself. It's already a value. This is our fun, our rule for functions. What's more interesting is what happens when we try to evaluate the result of applying a function. If we have an expression p and want to apply it to an expression q, what steps should we follow? First, we need to evaluate the expression p. It's going to evaluate to some function, we'll call its argument x, and the body b. Then we'll evaluate q. That's going to evaluate to some other value, we'll call that value vq. And now we've evaluated a function, and we've evaluated the function's argument. How do we determine the result of the function application? What we'll do is evaluate the function's body b, substituting any occurrences of the function argument x with vq, the value of the argument to the function. So for example, if we had the expression fun x arrow x times 2, 1 plus 3, we'd first evaluate the left expression, which is just a function to itself. Then we'd evaluate the right expression, 1 plus 3, to a value 4, following our existing rules. And then we'd take the body of the function, x times 2, and substitute occurrences of x with this argument value 4, giving us 4 times 2, which again evaluates to 8. These rules then make up the evaluation rules for many of the common parts of the OCaml language. But you may have noticed that our rules for evaluating let expressions and function application depended on our ability to perform substitution, such as when we took x times 2, substituted x with 4, and got the expression 4 times 2. In this case, the substitution is pretty clear, but substitution isn't always so obvious. So it will actually be useful for us to define a new set of rules to precisely define how substitution works. To be clear, what we're about to look at is an entirely different set of rules. So far, we've been coming up with rules for precisely defining evaluation, how to determine what an expression evaluates to. But since we've now encountered evaluation rules that require us to perform substitution, if we want to continue to be precise, we need a different set of rules for defining how substitution works. So let's do that. Let's define some rules for substitution. We'll start with some simple rules. If we have an integer m and we want to substitute some variable x with an expression q, the result is just that same integer m. There's no variables that appear in an integer literal expression, so there's nothing to substitute. If we have a variable x and we want to substitute some occurrences of x with q, then the result is that expression q. We're performing the substitution on the correct variable. But if we have a variable y and we want to substitute q for occurrences of x, where x and y are different variables, then we shouldn't perform the substitution. The result is going to be the same variable y. We only want to substitute x, so if we have a different variable, it should be left unchanged. And if we have some binary operator like p plus r, where p and r are expressions, and we want to substitute occurrences of x with the expression q, then we need to be sure to substitute all occurrences of x that appear in both the left expression and the right expression. So we'll recursively define this substitution as the result of taking p and substituting x with q, and adding r after substituting x with q. And we'll have similar rules for other binary operators too. By following rules like these, we can determine precisely what substitution means. To take our example from earlier, if we have the expression x times 2, and we want to substitute x with 4, how precisely can we arrive at the answer? Well, we have a multiplication of two expressions, so following our substitution rule, we'll apply the substitution recursively to each of the sub-expressions. We'll take x and substitute x with 4, and we'll multiply that by 2 with x substituted with 4. X with x substituted with 4 is our variable case. The variable in question is the one we're substituting, so the result is 4. 2 with x substituted with 4 is just 2. Our rule for integer literals says that they're unaffected by substitution, and that gives us our answer 4 times 2. Where the substitution rules get interesting, though, is when we start to look at substitution within a let expression. Here's an example. Let x equal 5 in let x equal 1 in x. Think for a moment about what that expression should evaluate to. Now, let's see what might happen if we try to apply our rules. We start with our rule for evaluating a let expression, our let. We take the definition, in this case 5, and evaluate it to itself. Then we take the body, in this case let x equal 1 in x, and substitute occurrences of x with 5. We haven't yet defined how this kind of substitution works, but imagine that we spotted that there's an x in the body of this expression, so we substituted it for 5. Well, in that case, if we evaluated let x equal 1 in 5, we'd evaluate the definition 1 to 1, and the body 5 with x substituted with 1 is just 5, which evaluates to 5, which is our final answer. We seem to have arrived at the conclusion that let x equal 5 in let x equal 1 in x evaluates to 5, when actually we know that it should have instead evaluated to 1. Something went wrong in our substitution. When we took the expression let x equal 1 in x and substituted x with 5, the result, let x equal 1 in 5, is the wrong answer. Instead, we should have kept the expression as let x equal 1 in x so that the expression would evaluate to 1. But how do we fit that into our rules for substitution? So far, when we've been talking about substituting x with some expression, we've done so wherever we see x appear in an expression. But to take variable scope into account, we shouldn't replace all occurrences of x during substitution, only certain occurrences. Here, we need to make the distinction between free and bound variables. A variable is bound if it's within the scope of some construct, like a let expression or a function, that introduces that variable name. For example, in the expression fun x arrow x plus y, x here is a bound variable, because it's bound by the argument to the function. Likewise, in the expression let x equal 8 in x plus y, the x here is bound, this time by the let expression. If a variable isn't bound, then it's free. So y in both of these expressions is a free variable. There's no construct like a let expression or a function that binds it. When we perform substitution, we only want to substitute free occurrences of a variable. We don't want to substitute bound occurrences of a variable, since some other let expression or function will be responsible for determining what that variable refers to. So, to be formal about this, we actually need a third set of rules now, a set of rules to define how to take an expression and determine what the free variables are. Let's write those free variable rules now. If we take an integer literal m, there are no free variables in that expression, so the set of free variables is the empty set. If we have a variable x, then that variable is the only free variable in the expression, so the set of free variables is the set containing x. If we have the addition of two expressions p and q, there might be free variables in either half of the expression, so the set of free variables is the union of the free variables in p and the free variables in q. The same could be said for other binary operators too, and it's also true of function application. If the function expression p is applied to the argument expression q, free variables could appear in either the function or the argument, so we need to take the union of both. What about the free variables in a function by itself? like a function whose argument is x and has a body p? Well, we could first compute all the free variables in p. But if the variable x appears in the body of the function p, it shouldn't be a free variable, since the variable x is bound by this function. So in this case, we'll need to be sure to subtract the variable x from the set of free variables if it's in the set. X should not be a free variable here. The story is similar for a let expression, like let x equal p in q. We can compute the free variables in q, but any occurrences of x that appear here are going to be bound, not free, so we need to subtract the variable x from the set of free variables. And then we can take the union of the free variables in the definition p. Here we don't need to subtract anything. Any variables in p are free, since a let expression only binds its variable in the body of the let expression. These rules formally describe how to take any expression and determine what the free variables are. But let's now take a step back and remember why it is that we're defining these rules at all. We started with trying to define a set of rules for evaluating expressions. But some of those rules required performing substitution, so we needed a set of rules for substitution. And some of our rules for substitution required knowing which variables are free and bound, which led us to define a set of rules for free variables. With those rules for free variables in mind, let's now revisit our rules for how to substitute in a let expression. If we have a let expression, let x equal q in R, and we want to substitute that x with p, what we know now is that we shouldn't perform any substitutions in the expression R. If the variable x appears in R, it's a bound occurrence of x bound by this let expression. And we know we only want to replace free occurrences of variables, not bound ones. The only place where free occurrences of the variable might appear is in q. So we can say that we substitute the expression as letting x equal q with x substituted with p in the expression R. What if we had a let expression let y equal q in R, and we wanted to substitute occurrences of x with p? Now the variables are different. The let expression is binding the variable y, but we're substituting the variable x. Since x isn't getting bound by this let expression, we can substitute x in both q and in R. All of the occurrences of x are free. For example, if we had the expression let y equal x plus 2 in x plus y, and we wanted to substitute x with 1, we would do that in both the definition and the body of the let expression, and we would get the expression let y equal 1 plus 2 in 1 plus y. Actually, though, there's still one minor problem with this rule. Let's say we had the expression let y equal 10 in x plus y, and we wanted to substitute x with the expression y plus 1. Intuitively, we know that this binding of y to 10 should only apply to y's in the body expression, which in this case would be this y at the end of the expression. But if we were to use our substitution rule here, we'd end up replacing x with y plus 1, and we'd get let y equal 10 in y plus 1 plus y. We've taken the y that wasn't bound before and suddenly made it bound. What was the problem here? The problem was that in the original task, to take the expression let y equal 10 in x plus y and substitute x with the expression y plus 1, the variable bound by the let expression y also appears free in what x is being substituted with. As a result, during substitution, we inadvertently turned the free variable into a bound variable. These two y's are different variables, but we ended up treating them the same. The solution then is going to be to swap out the variable in the let expression for some fresh variable that hasn't been used yet. For example, we might substitute y with z and get let z equal 10 in x plus z. Then, when we perform the substitution of x with y plus 1, we get let z equal 10 in y plus 1 plus z. We've successfully performed the substitution while making sure that the variable y is still free and didn't get captured by the let expression. We can formalize that into some rules. The rule we've written already works when x and y are different variables, but only when y doesn't appear as a free variable in P. If y does appear in the free variables of P, then we need a fresh variable z. We'll convert the let expression to be a let expression with z, and in the body of the expression, we'll convert any of the y's to z's first before we perform the substitution of x with P. The same thing we just did, now just stated as a more general rule. Since functions also bind variables in much the same way as let expressions, their substitution rules are very similar. If we're substituting a variable that's the same as the variable bound by a function, we don't perform any substitution. But if we're substituting a different variable, then we should go ahead and perform the substitution in the function body. And in the case that the function's argument variable is also a variable that appears in the expression that we're substituting for x, then we need a fresh variable z to avoid the same variable capture issue. So let's put all these pieces together. Say we had an expression like let x equal 1 in x plus let x equal 2 in x. To evaluate this expression, we first evaluate the definition of x to 1. Then we evaluate the result of substituting x with 1 in the expression x plus let x equal 2 in x. Following our substitution rules, we know that we need to consider both halves of the addition, and x will be substituted with 1, but let x equal 2 in x shouldn't have x's substituted, since the occurrence of x is bound. Now we have an addition expression, so we'll evaluate the left to 1, and we'll evaluate the right, let x equal 2 in x, by first evaluating the definition 2, and then evaluating the result of the body x with x substituted with 2, which gives us 2. So we have 1 plus 2, which gives us the answer of 3. By using all of these rules, our rules for evaluation, substitution, and free variables, we now have a formal semantics for understanding what expressions evaluate to. That said, we still haven't considered the entire language yet. There are booleans and conditionals to consider, for example, but also, notably, there's one other important construct we haven't looked at yet, recursion. Say we had defined and tried to use the factorial function, recursively defining f to be the factorial function in the expression f applied to 2. How could we compute the factorial of 2? Well, if we used our existing let rules, we would evaluate the definition of f to get a function, and we would end up substituting that function for f. But now we have a problem. In this new expression, the function makes reference to a name f, and based on just this expression alone, we have no idea what f should be. What should we replace f with in our new rule for let rec? Our first instinct might be to replace f with a copy of the function again, but that just postpones the problem. We'd end up with some larger expression that contains an unbound f that we eventually might arrive at. In the spirit of recursion, the solution is going to be to replace f with another let rec expression. Let rec f equal the function definition in f. Now, f is defined as the appropriate function, so we don't have to worry about it being unbound. And since we're using a let rec expression, when we eventually need to evaluate that expression, we'll use this same let rec rule to replace any future occurrences of f with another let rec expression. This guarantees we can keep calling f recursively until eventually we stop computation by evaluating some expression that doesn't require calling f. To formalize this into a rule, we want to evaluate the expression let rec x equal d in b. First, as with before, we evaluate the definition d to a value vd. And now we evaluate the body. But instead of just substituting x with the value vd, remember that the value vd might recursively make references to the variable x. So we want to first substitute x with the expression let rec x equal vd in x, so that x both has the correct value and will have its future occurrences substituted appropriately. That body expression gets evaluated to a value vb, and that value is then our answer. We've seen a lot of rules now, rules for how to evaluate expressions, rules for how to substitute in expressions, and rules for how to find the free variables in expressions. But taken together, they allow us to formally define a semantics for our programming language, so that we have a precise way to know what any expression in the language really means.